Shall we start?
Yeah.
Yes. Are you ready, Rex?
Yeah.
Okay. Tell me when we are live. So, good afternoon and welcome everybody to the Institute of Astrophysics. For the National Space Day, we are celebrating National Space Day today to commemorate the first anniversary of the landing of Chandrayaan 3 rover and lander on the moon's surface exactly a year ago. And we have a nice set of programs for you. First, we're going to have a talk by Dr. Rekhesh Mohan, followed by a short intermission where we're going to release some images and flyers and also distribute prizes for the quiz which happened earlier today morning, followed by a talk by Dr. Seetha, who's sitting here with us. Okay. So the first talk of today will be with Dr. Rekhesh. Rekhesh works here at the Institute of Astrophysics. He's an astronomer. He got his PhD in astronomy from Raman Research Institute in Bangalore here. He did his master's from IIT Madras and his bachelor's from Cochin, right?
Yes.
Yeah. His thesis was on radio astronomy using the Giant Meteor Radio Telescope, which is in Pune. I think that was a question on the quiz in the morning. Following which, he's been using a number of telescopes in India and elsewhere. He joined here in 2005. His expertise is in radio astronomy, ultraviolet astronomy, as well as instrumentation for space astronomy, which includes making small payloads to fly to space, either through satellites or through balloons. He leads the group here in IIA, which builds low-cost space payloads for ultraviolet astronomy, and they're currently developing ultraviolet imagers and spectrographs for mapping the sky in the UV. They also developed a very versatile low-cost star sensor using Raspberry Pi, which a lot of you might have heard of, that can be easily customizable for a wide variety of requirements in space. So now Rekhesh Mohan will talk to us a little bit about what we do in this institute about space astronomy, and also why we had to go to space in the first place. So I will, it's around 25 minutes, right? And then we'll have 5 minutes for questions, both from here and people who joined us online. Yes, please.
Thanks. Alright, so we're running a bit late. So anyway, so let me get started. So, astronomy is all about, it starts with gathering information from outside the planet. That's how we started a few hundred years ago, maybe 1,000 years ago. Look at moon, sun, planet, comets, asteroids, and then move slowly outside the solar system. There is the realm of galactic astronomy, about our galaxy. Look at stars, star clusters, stellar remnants, stars at different stages of their evolution. It's like, astronomy is one of those sciences where you can't tamper with the setup. You can only observe from a distance, right? So if you want to study how stars are evolving, you don't have time to monitor one star through all the evolution because it's going to take millions of years. That's your mode. Instead, what we can do is we have a sample of stars at different stages of their life. So we can sample through that, observe them, collect data, and then put a story together, try to understand what's happening. Similarly, the material between stars, the dust and leftover gas, which is going to scatter starlight, you can study that. And then you go beyond the galaxy, other galaxies, cosmology, universe as a whole. So there's a lot of information here. And after we gather this, we need to now find out what is going on. By the way, astronomy is not just taking photos of these objects in the sky. You also can look at the spectral information. Like here's a spectra of the sun with what you get when you use a prism or something to disperse the light, right? So if you can zoom into this region, you can see there's more features in this. And now with this region here, there's the wavelength in nanometer. You see that individual lines. So there's a lot of information coming through. The spectral lines advantage is that if you can compare that, if you identify the lines from which species it's coming from, then you compare with the frequency of this line in the lab and compare the frequency at which you measured it. The shift can tell you the relative velocity between the observer and the emitting source, absorbing source in this case. You get emission lines also, that's another scenario. And the width will tell you the velocity distribution of the material that is absorbing this. It's basically Doppler shift. There's a lot, the with the velocity, there is Doppler shift of each individual photons absorbing here, and that will tell you something about the physics of what's happening there. Now that's about the spectra, but it's again not just images and spectra. We also have, you study the variation of light with time, transients, variability studies. Like this is an example of an exploding star, where the brightness goes up and then slowly decays down. So if you keep observing this source over the days after maximum brightness, almost a year, you see that it is varying. From this information, you can build up a story of what is happening there, why is it happening. And here is a picture of a star and a planet moving in front of that. So if it's a large enough planet or a small enough star, when it moves in front, it blocks some of the starlight, right? Because planets don't emit light, they are only scattering the starlight. So when it comes in front, it's actually blocking the light. So it dips, the light from the star dips. It's a small fraction, this is amplified greatly. You get a small fraction of a percentage, but you can measure it. From that, the time over which it is dipping, you know the time it takes to cross this. From that, you can infer something about the orbit of the planet around the star. So, the universe is sending us a lot of data. There's information everywhere. Now, how can we gather most of it? The more we collect, the better idea we get about what's happening, right? So it turns out that the information coming to Earth is affected by the atmosphere. So this is the amount of light it blocks. The atmosphere blocks as a function of wavelength, the different parts of the electromagnetic spectrum. So at very short wavelength, you can see it blocks all the light. The reason is, it's mostly because the light, the energy of the photons is so large that it will ionize the atoms in the atmosphere. So once the photon is absorbed and when the atom is ionized, you lose that information, right? It may be scattered in some other direction, emitted. But the opacity is less in this short region here, that is our visible wavelength range, what we see with our eyes, and it again fluctuates, and longer wavelength, shorter frequencies, the radio is again transparent. So, problem is, a lot of this information that comes through is either blocked or affected by the atmosphere. We have only these bands where we can actually collect. Even in this band here, even though its light is coming through, the turbulence in the atmosphere and other factors can actually distort the light. So that's again the problem. You'll have to understand that effect and remove that to finally extract the information coming from above the atmosphere, right? There's a lot of processing involved in that. But so this is roughly what astronomers do from the ground. But to collect information in other wavelengths, we have to go to space. We have to go above the atmosphere. That's why we have space telescopes like these. Right? Now that brings us to the space astronomy, which is observation from above the atmosphere. The easiest thing to do would be to go above the atmosphere, a little bit above the atmosphere, which we call the low Earth orbit, which is relatively speaking not too expensive nowadays. But you have it, like this is an example of this is a space station in a low Earth orbit, and you can see that the size of Earth is pretty large because you're only around 600 kilometers above the surface of Earth. So this Earth is quite bright. It scatters light, sunlight, and quite bright. And there are also this other glow from the atmosphere called air glow, and there is geocoronal emission, a lot of other factors. So when you observe from the low Earth orbit, you have to be careful of these things. You have to avoid this and observe away from this light, away from this emission. And the good thing is you are not very far from Earth. So when you observe, you are collecting data, right? So you need to transfer it down to the ground. That is relatively easy here. But to avoid these things and also to have a stable orbit, one way to do that is to go to Lagrangian points. So you could also go to geostationary orbit, but considering various factors, you have to justify the cost involved in going to that. If you can do it in low Earth orbit, better. Lagrangian points are this. There are 5 Lagrangian points for the Sun and Earth, any two bodies. These are the points where the gravitational field, the gravitational force from these two objects, plus the centrifugal force of this point or anything in this point moving around, they balance out each other. So it's like a stable location. Once you reach there, you don't need much of fuel to keep that in place. It can stay there. It's easy to understand L1 and L3 because there could be a point in the center of Earth, but yeah, equivalent of that is other side of the orbit, right? We are away from Earth. This is like where the gravitational forces are balanced. Other three are, it involves centrifugal force as well. But yeah, so these are the favorite points for astronomers if they want to do, for example, infrared observations of the universe or any other sensitive observations, and you want to keep less fuel for maintain that orbit, then you can go to these points. But the trouble is reaching there is expensive. It takes months to reach here. You need enough fuel in the rocket to send you there. And since you're far away, the communication also becomes tricky. Okay, now the space astronomy at IIA, what we are doing. It started in 2000s, almost the same time when AstroSat also was being discussed. So this was a UV telescope which was supposed to be, this is a geostationary satellite. Idea was that to use this space on the satellite, which is Earth is in this direction, so it's away from the Earth. You can mount it here, this payload here, which is a set of 3 UV telescopes designed to scan the sky. When this satellite is going around Earth, this is going to scan the sky in this direction, right? So it collects data from all over the sky, which you can later put together. So it was designed for sky surveys, and unfortunately it didn't succeed. It was abandoned somewhere close to the launch, but it was a great learning experience. Personally for me, like, as Neeraj said, I did my PhD in radio astronomy. And then I moved to UV astronomy in IIA, and this was a great learning experience and an introduction to instrumentation, as well as, you work with our space agency, ISRO. Like, the difference is that in academia, we tend to have, you have enough time to experiment those things. You can play around, you can make mistakes. But when you're working with the space agency, they're working on a project mode. So they have deadlines, you have to meet that. So it was a different experience for me. So this is how most of us started here. And almost same time this AstroSat was taking shape. The initial discussions started in late 1990s. The preliminary design was around 2005 or 6. And finally it was launched in 2015. So just not the time scales here. Like it takes more than 10 years to build it. And one of the main challenges in this is because you have X-ray payloads here. This is UVIT, which you might have seen there, engineering model. There's another imaging telescope in hard X-ray. There's a soft X-ray telescope and a scanning sky monitor. So there's a lot of this coordination, interfaces, data. There's plenty of challenges. So it takes a long time to put this together and ensure everything is working. Because it is a large mission, you can't afford to take risk. There's a lot of money involved, so you have to check everything, ensure that everything is working properly. Only then you can launch. Because once you launch, you cannot change it. Right? You can't go to space and repair it or anything. Unlike a ground-based observatory, you have to check everything. That's the main challenge in space. Even there are even unexpected things you would learn from this. Yeah, okay, I'll come to that. So UVIT is a very sensitive ultraviolet imaging telescope, right? And there's also the scanning sky monitor here. This is actually, it's scanning the sky for X-ray transit. It keeps rotating like this, scanning most of the sky. Now, unlike something on the ground, this is floating in space, right? It's not anchored to anything. Right? It's here. And I have a turning thing, scanning sky monitor here. This could actually, when it turns, It can create a jitter on the satellite, which may not happen if it's anchored onto a table or something, but it's floating in space. So these are the new things you have to think about when you plan it. So this is an example of what happens. This is the shape on the satellite because of this movement of this thing. See? It's like a ringing phenomenon. Fortunately, from the images you can see the shift in start positions when you're imaging it, and then you can calculate this and you can correct for it, which is fine. Yeah, so this whole thing of UVIT it consists of two twin telescopes. You might have seen it here, two tubes, and one is for far ultraviolet, the other one is for near ultraviolet. Plus, there is a visible channel detector also, that is to measure this drift and all that. It's not used for any science, it's to correct for the drift. It was designed and built in IIA, and Institute had to build new facilities to build this telescope here. This is one of the clean rooms. You will hear more about it a little later. You can see this is a two telescope tube, people are working on it. And to some extent, I would say this is how the space astronomy started in India and IIA. Because AstroSat, after launch, it has been, and the whole world has noticed that India's mission is producing world-class science. There's more than 300 publications, I think, right now. It's still observing, it's in orbit 10 years later. So this is how it started. But yeah, so near UV channel stopped working sometime in 2017, but the far ultraviolet channel is still working. So since this is a very sensitive instrument, there is a certain part of the sky which you cannot observe, it's too bright. It can trouble the detector. Like this is the plane of the galaxy. This is an all-sky image of the sky, and this is the plane of the galaxy. And most of the UV telescope has not covered it because it's too bright. A lot of these bright stars, scattered light from dust and gas. So this region is not observable with the sensitive instrument like the UVIT. And now shifting focus from there. I just mentioned that it is too, and the instrument is too sensitive to observe some regions of the sky. Other payload which happened more recently is the Aditya L1, the visible emission line coronagraph on this mission was built at IIA. While initial discussion started in late 2000s, the idea was to have image the corona of the sun and have some spectral studies of this. But the challenge here is different because the sun is too bright. That much light can actually burn everything inside. So we need to find ways to block it. Like during a total solar eclipse, moon blocks the sun, right? But we are thinking of the people who are building it wanted to block it all through the mission lifetime. So they need to block the sun and study the rest. So that was a major challenge. This is the whole mission here, the whole satellite. On top of this VLC, and there's also this ultraviolet imaging telescope for the sun. And other instrument to measure the charged particles in situ, near the location of the satellite. So as I said, this was an engineering challenge. Another challenge is to manage the heating due to the sunlight. Sun heats everything, right? Unlike what we have in this room, you have air which can convect the heat away. But when you are in space, there is no air. It's very difficult to take the heat away from any of these elements inside, which is getting heated by the sun. So you need to have radiative plates like this here, carry the heat away, and you need to have fallback mechanism in place to protect the sensitive detectors. And this mission was sent to L1. It's a stable orbit here. So and the challenge of ensuring that it is pointed at the sun all the time, that was taken up by ISRO. And the challenge for making sure the instrument works, in spite of all the heating, that was IIA's responsibility. And there are a lot of these optical elements on a platform like this. It was, and I'm sure the engineers in IIA learned a lot from this mission because it was unlike anything people have taken it up before this. It is now operational, it's in orbit. Now, let me come to something else now. Those were big missions. If you notice here, I was talking about large time frames. It takes a long time. It was launched recently. Now, there are also, and right now there's a lot of interest in this kind of small missions. These are basically called CubeSats. And these are payload to address, so science from astronomy point of view, these are payloads which can address specific science cases. It's not a general purpose instrument like UVIT, but it's easy to build. So this is some of the things that we have the clean rooms where UVIT was assembled. We also have other facilities to build all this required things for small payloads here. So this is what I was talking about. The CubeSats, they measured in terms of U. 1 U means it's 10 centimeter cube. For astronomy payload, we need at least 3 U. Okay, so that the mirrors or lenses and all take up this 22 U here, and some part for the electronics. We have to collect the data, we have to send it to the satellite, which then transmit to the ground. And the typical mass is much less here, 3 kg to 20 kg, that range. Relatively less power consumption, and lifetime is also less. But you design it to address a specific science case. Address the science case and lifetime is over. But it's much cheaper to build it. So this is our small payload group here. What we are focusing on is student-led projects, supported by all the expertise we have in IIA. The development time is much shorter, 3 to 5 years, compared to the big project which took more than 10 years. And right now we have easier and cheaper launch options for small payload, because everything depends on the weight of the payload. If you have massive payload, you need to pay more money for the launch. So the kind of things we can undertake is sky surveys, for example. As I showed earlier, the galactic plane was not observable with sensitive telescopes. So we can do that with a small one. We can do long-term monitoring of transients, which big telescope may not have time to keep looking at one particular area of the sky. It will have a lot of other things to do. Small missions are okay. Now, these are some of the things we are planning, which complements the large telescopes. So, and also what is equally important is when you are looking at ways to optimize science for the amount of money you invest in, you have to look at innovations. So as we develop this kind of small payloads for astronomy, we need to have innovative designs and subsystems to keep the cost low, ensure that it works, and get the science you need. And the space industry in the country is undergoing a massive revolution right now. 15 years ago, it was only ISRO, right? And now a lot of other people are coming into the game. They're developing new rockets, new satellites, planning ground stations. So what we are thinking is, of course, that is their job. But we have to innovate to ensure that our science is done in an affordable cost, right? So what we are doing is, we design and develop and test qualify for our requirement. Once it is done, we are going to share it with everyone. Let everyone in the country benefit from that. That's the policy we are following. We also have collaborations with other institutes and industry, like IITs, IIC, private space industry as well. So we are bringing together all these people, do some science, and whatever we develop, we are going to share it with the industry if they are interested in. It's all open source now. Yeah, this is some of the examples of innovations. For example, every payload needs an onboard computer which has to acquire data, do some initial processing, store it, transfer it to the satellite side, or maybe receive commands from the satellite, execute it. For example, when to start observation, when to end the observation. These are all ground commands, right? So then it needs some amount of intelligence and computing power on board. Traditionally, all the space things are done with expensive space-qualified hardware, which is shielding, and they use expensive FPGAs for that most of the time, field programmable gate arrays. What we are trying is to use a commercial single-board computer called Raspberry Pi. It's much cheaper. And people in NASA has tested it in space, and it seems to survive. And for the data acquisition and transfer, we are using a microcontroller. This also again it's a cheap microcontroller, but it works. There's a paper for that. And also for the onboard data processing, we are using Raspberry Pi again for that. These are all being tested, and it seems to work. And the other thing which needed mentioned is the star sensor. See, when your satellite is in space and it is drifting in space, you need to know where you're looking at, right? And you cannot use a GPS in orbit. So we have to look at stars around us. So what is star sensor? The basic functionality of star sensor is take a photo of the sky and then identify the location of stars, compare it with the known catalog of stars, bright stars, which is stored on board. By comparing these two, you know that this is the location of the bright stars, then you know which location it is pointed at. Right? This is how it calculates the coordinates of look direction. This has been used in all the satellites and even some of the aircraft. But what we have done is, again, use a very cheap computer and still ensure that, with some optimized programming, ensure that it gets a near real-time information of where we are looking at. This much is around 10 centimeters. It is a small image. This is another one which we built last year, and it was tested last year April. This is the PSLV C55, and ISRO had this platform here. This is the fourth stage of the rocket, and there's the main satellite. So once this stage goes into orbit and ejects the satellite, the rest of it is going to stay there. So they've given this platform where you can put small experiments. For a few days' time, it will be in orbit. So we tested it there. This is the image of the sky it made, and of course, this is how the unit is sitting on the inside this. After some time, there was no control over where it is looking, so it turned to Earth also. And these lines here are due to data transmission errors, like I said. So it worked. And the point is, for 3 to 5 days, the platform was stabilized. Afterward, the platform was not stabilized, but this kept on giving the data, which is of no use because it's tumbling very fast. But it worked till as long as the platform itself was alive, around 6 months. So we are confident that the star sensor can work in space. Yeah, and some more things which we are trying to do indigenously is that, when you work with space, many things may not be readily available. For example, this slit is, if you have done experiments in the lab, you actually block most of the light with the slit, right? And then you disperse that light. So we needed this slit of 25 micron width, variable width, 25 micron in the middle. Turns out there were no vendors in India who was going to build it. We didn't have expertise here. People could do up to 50 microns, but not 25. We checked with international vendors. There are people who can build it, but they refuse to give us because it is space UV. So there is certain things that are export restrictions. So then what do? We actually found that some department in Bangalore, IIA, they had the equipment, but that was not meant for slips. But we explained the situation to them, explained what we need. They agreed to try it, and then they managed to build it. It was not on a regular kind, not a regular stage. They are comfortable working with silicon substrate. It's very brittle, so it's not easy to handle it. But we managed to glue it onto a metal slit, and then that worked. Tested and qualified. It's working beautiful. So this is the kind of another way of reducing the cost and also engaging with similar institutes in the country to get our work done. So now I was talking all about what we did from AstroSat to small payloads, but something which we often forget is that right from India's first satellite, which was sent to space in 1975, we have been building payload to conduct experiments in space. The first satellite had a payload to do X-ray astronomy with solar physics. It didn't last long, only 4 days, but it was there. And then Bhaskara 1 also had an X-ray sky monitor to detect transient X-ray sources. And later in 1994, there was a payload to, these are not primary payload, these are secondary payload for other satellites. But there was a payload to detect and study gamma ray bursts. And this one actually discovered 12 of them. There were, I think, close to 1,000 triggers, possible detection, but after careful analysis, they found only 12 of them were genuine. The rest of it was false trigger. And then a bit later, 1996, this is a remote sensing satellite, but it had a payload on top called Indian X-ray Astronomy Instruments. This was highly successful, more than 30 publications. You can see that slowly we are gaining experience, we are building better instruments, doing better science. And GSAT-2, another geostationary satellite, had a solar X-ray spectrometer to study. So, it's not like we suddenly start building AstroSat and VLC and all this. There's a heritage. We learned it slowly. We means astronomers in India working with ISRO. Okay, and the future is a lot of things being planned. For example, a 1 meter UV space observatory, which IIA is leading it, called INSYST. And IIT Bombay is leading a collaboration to detect high energy transient. There are 2 of these satellites which scans most of the sky to detect energetic, high energy events, transients and all. ExoWorld is another 1 meter class telescope to study extrasolar planets, detection and characterization. So now recently there's a lot of talk about astronomy from the moon. There's a worldwide interest in setting up observatories on the moon. The reason is, it's a stable platform, there's no atmosphere, no disturbance from atmosphere. And it turns very slowly, so you have long nights, you can have a lot of observation. Even in the daytime, you can observe part of the sky because there's no atmosphere, no scattering. But a lot of feasibility study need to be carried out to assess the conditions before we send an expensive instrument. This is what I'm trying to convince people. So we'll start with small payloads, send it to moon and see how it works, and then we plan for a bigger one. So yeah, this is the kind of things we're doing. We're slowly pushing the boundaries to explore further into the universe. Thanks. So these are some of the URLs which I mentioned today, and you are particularly interested. Thank you.
Thank you. Thanks, Rekhesh Mohan. I think I want you to go back to one side, which I thought was the really interesting thing for people here, especially the students.
Yeah.
What he cannot know, your poem.
Sorry.
Huh.
Yeah.
So what I think wasn't, I don't know if it's was clear was that, so they in this lab made a really small instrument, 3D printed, right?
Not 3D printed.
Okay, the thing there, right, which looks like a lunchbox, right?
Yes. This one here.
Water bottle. They made it here and they sent it to ISRO and ISRO flew it for it, right? And then it was in space and then the pictures that was taken by that small little instrument in space and sent back here, and the students here actually did work on this data, right? So that's something really exciting, isn't it? That you could actually, in a lab in Bangalore, make something very small, very easy, send it, and then ISRO sends it to space, and then you can actually look at, observe things yourself, right? And you get data from there, and you can do it yourself. That's really cool, right? So I hope that, and now many schools and colleges are starting these CubeSat programs and so on. So I hope your schools also start that, and you can come and talk to us about it. So we'll take a couple of questions. We have one question from YouTube, but then people on YouTube, if you have questions, you can type it there, we'll take it, but any quick questions from here about anything he said? Yes, you please, then you. Tisha will pass the mic.
It's not on. It's not on.
One of them is on.
Not that.
Thank you for the interesting talk, sir. I'm Kumar's mother.
Okay.
I have 2 questions. First question is, you mentioned that Aditya is in L1 point,
Yeah.
but the problems you faced were that it has to always be covering the sun, and also the sunlight is causing a lot of heat.
Yeah.
So why was L2 not chosen? Because both these problems would have been solved.
No. Okay.
And second question is, how can we get started with either radio astronomy or CubeSats?
So let me answer the first one. L2 also is and you're moving further away from the sun, but the same problem will be there.
But
Like
Earth's shadow is there.
yeah, then we can't observe the sun. No? If we're in the shadow, we won't see the sun.
Not even covered like the corona part.
No, because Earth is very big. Right?
Okay.
So then you won't be able to see the sun. If you're in the Earth's shadow, then first of all you won't get enough power. The solar panels will be in the shadow. So it's not suitable for studying the sun. You need to be directly looking at it.
Okay. JWST is in L2, I think.
Yeah, but that is for nighttime observation. They don't look at the sun. That will burn the instrument.
Okay.
Yeah, about second thing about CubeSat, I think since there are some teachers here as well, maybe I can rephrase the question. If schools want to develop their own CubeSat programs, what kind of support would your group be able to offer?
We can discuss it. We are open to any kind of discussion. If you have an interesting science case or something you want to do, and you have planned for this, we can help you build it. And then look for launch opportunities. And
Or even balloon flights.
balloon flights, yeah. We also do a high altitude balloon experiment. We have permission to launch balloons. So if you have any interesting ideas for that, you can do that also. And in fact, a few schools have done it with us. I forgot the name of the school. That school, the students, so high school students, they wanted to see how the ozone fraction varies with the atmosphere. So they put a small, it's a very cheap ozone detector, and we flew it on that.
He's very much
Yeah.
interested in all space and astronomy.
Okay, yeah,
He
yeah.
does it.
Yeah, so we'll go to the next question. Yeah, please.
We can discuss
Yes,
later.
the person, gentleman in front.
Thank you, Rekhesh, for your interesting talk. It's very basic question. I'm not into astronomy or science or anything like that.
Can you exchange the mic? I think this one is not working.
Yeah, the other one is.
Yes. My basic simple question. Why are you interested in building UV telescopes? I mean, what is the significance of UV telescopes? Why not other wavelengths?
Yeah,
That's one
so,
question.
Okay.
The second one is you said we are using, not using, rather we can use a Raspberry Pi,
Yes.
right? That is the two that is off shelf available Raspberry Pi.
Hmm.
And you say it survived or somebody tested it, but that is inside the box of the satellite. It can work.
Yeah.
Is that what you
Yeah, yeah. It's better. We don't need to put it outside.
Outside.
We'll have ensure some shielding is there.
Ah.
We have to ensure it works.
Oh.
So the first question was why UV astronomy? Right? See, IIA has optical astronomy, for example. A lot of it can be done from the ground. So that we are doing. Radio also we have observatories. X-ray astronomy, there are other groups in India who are experts in that. They are building X-ray payloads for space. Like I showed, we have a heritage of X-ray observations from space. UV astronomy is the most unexplored regime in the whole electromagnetic spectrum compared to others. So now we have that expertise. We have the labs here to build UV instruments. We also have a good team of scientists here, so there is a science motivation. We have the expertise to build the instrument. So it's a good combination, and it is compact. We can use small payloads for that.
I'm going to take one last question, quick question from online, then we'll have to move on. Question from Akash Simha. Is there a program for the star sensor? Is the program for star sensor open source? Where can we find it?
Yes, so it will be open source eventually. We are working on that. The code is right now in our Git repository. We'll make it public soon.
Okay.
The
Thank you.
code and the design.
Perfect, fantastic. So you can look at our website for more details later. Let's thank Rekhesh Mohan again. Before that, I request Seetha to. You can give.
Oh.
It's a picture of our observatory in Hanle in Ladakh. Thank you again, Rekhesh. Some merchandise. So again, if you're from a school and if you want to explore options of building CubeSats and doing small things, please contact us, contact them or contact us. And I think that's something we can start thinking about on National Space Day. Now we're going to have a half an hour break where we're going half an hour interactive where we're going to release some things and also do prize distribution. Then we break for tea and then we come back and we have the public talk by Dr. Seetha. Now, first we're going to do is, can we do, open the link, is it? How many of you saw the big telescope downstairs, which we have? Oh, awesome, great. You have seen it very nice. So you were told what that was, right? It's an exact replica of a telescope which is actually working in space right now, right? It's amazing, isn't it? And that's the ultraviolet imaging telescope built in Hoskote by our institute in collaboration with ISRO and other astronomers. Now you have seen, you know the Hubble Space Telescope, the James Webb Telescope, and so on. And you know them through their pretty pictures of stars and galaxies and nebulae and clusters they put out. We probably haven't been putting out that many images very much, and therefore, but then we know that the images taken by the ultraviolet imaging telescope are really beautiful. They're really pretty. They have a lot of science in them, but they're also beautiful to look at. And we thought it's time we shared them with you. And therefore, we created a Flickr account after really a long time. IIA is now young again, and we're starting with a small UVIT image gallery, which we want to release today on National Space Day. And I can ask Ishwar and Rekhesh and Seetha to kind of come here. Just leave it there. Okay. Yeah, can you just come here? And Rex, no, just leave it. Yeah, you can.
How many images are there on there?
Right now we put a few. So maybe let's see all the text. Just scroll through them and you can click on the first one. So what we put up a few images. You can click on the first one. This is on the Flickr account, iap.scope. And if you click on each one, you go down, you go below.
I'm not going below.
Use the mouse. Huh?
There's a mouse. There's a mouse.
Huh.
Yeah, now I can.
Yeah, I can. Go below. So there's a short description about each object. So we tell you what the name of the galaxy is, how far is it, which constellation it is in, why is it famous, what's special about the object, so a few details. And then we link to a Wikipedia page if there's a Wikipedia page. And then, but remember, these data are taken by astronomers to do something very specific, right? Astronomers all around India or the world. Prajwal is here. Can I ask him to also put up his hand?
Yes.
So Prajwal is the one who made all the images. So no, if you think they're pretty, please applaud for him. And so we have now, if you look at the album and just scroll, and so therefore, if the astronomers use this data to publish a paper, we also link the paper. That's a bit more advanced information, but we like to, you can read that as well. And then you can just go back to the album, just scroll down. Oh, that's not us.
This is not okay.
That's iStockphoto.com.
This is Flickr, I forgot that. Once you open the web, there's too much comes.
Yeah. Now, while he's doing that, I would like to ask Seetha to come just give a 2-3 minute explanation of why UVIT is special and why the imaging gallery is special. Yeah. I just scroll through them later. Are they nice? Are they pretty?
You all saw the model of the UVIT, right, on the ground floor. That's the UV telescope which was built here along with, as he said, ISRO and Canadian Space Agency. And this imager has 3 channels: NUV, NUV, FUV, and optical. Optical is mainly to correct the jitter, etc. Now, the thing is, this telescope, although very small compared to other telescopes in space, which can do UV astronomy, the advantage of this telescope was that it has a field of view of about half a degree. Half a degree, if we are to tell, it is approximately equal to the diameter of the moon. Okay, so a half a degree field of view, but a resolution of 1.2 arc seconds or so. 1.2 arc seconds, when I have to convert, that is about 1/1500 of the diameter. If you break up the diameter of the moon into 1,500 parts, how small would it be in space? That's what it is. And the thing was, the earlier satellite, which was similar to this, which could image galaxies as a whole, was Galax. And it had a resolution of about 4 to 5 arcseconds. So this UVIT is 4 to 5 times better than that. At the same time, it has a large field of view. So what it means is, for example, to tell you in simple terms, if I put my 2 hands here and look at this audience, it would be, I would not see this part of the audience, right? I would see only this part, right? And then I would have to turn here and turn here, turn here to see the whole hall, right? That's what many of the bigger telescopes do. For example, Hubble Space Telescope has a very, very fine resolution and it can do UV, but the field of view is small. So it has to do multiple imaging to completely get the picture of a galaxy. Whereas the UVIT may not have as good a resolution, but it can picture galaxies within if it's bright enough, few hundreds of milliseconds. In fact, that NGC 2336, the first image, was within few hundreds of milliseconds. Or you can just look at it for tens of minutes, and within 20 minutes you can get a good enough image going down to 20th or 23rd magnitude. So that's the big advantage of UVIT, and therefore astronomers can study clusters of stars, resolve the stars in these clusters, resolve star-forming regions in galaxies. In fact, he has worked on star-forming regions in galaxies, identifying where are the star-forming regions in the spiral arms, etc. So that's the advantage of UV. And we could do it both in NUV and far UV, but now the NUV is not working, so now we can do it only in the far UV. And far UV is very important. Somebody asked, why do you do it in UV? The very hot stars, hotter the star, they emit more in the shorter wavelengths. So if you want to study stars with a temperature, see our sun, what is the temperature?
5,600 Kelvin.
Very good. So that emits prime, that peak emission is in yellow light. Whereas if you have a star with a temperature of 10,000, it would be in bluer light. Okay? And if you have temperatures of 20,000, 30,000, etc., you go to ultraviolet, right? So, to study very hot stars, and hot stars are young usually, and they are also massive, and they are very luminous. All these go together if you and why did I say star-forming regions? Many of the star-forming regions have these young stars glowing in ultraviolet. And so it's easier for us to pick up these star-forming regions in ultraviolet. So that's why we go to it.
Thank you, Dr. Seetha. So now you realize why this is such an interesting image gallery. If you can now go look at it yourself on Flickr, you can find us as Indian Institute of Astrophysics. If you look at a galaxy's picture, and then you can also look at the same picture of the same galaxy from Hubble Space Telescope, right, online. You compare the two, they will be a bit similar, but not exactly. And the difference is because, like she said, HST, the Hubble Space Telescope picture will be about stars like our sun, whereas this will image stars which are much hotter than the sun, right? And therefore the young stars which are being formed, which are very much hotter. And therefore you can actually go and look at the HST versus UVIT picture yourself, and then you can kind of figure out what the differences are, where the differences are, and why the differences are. And you can, under each galaxy, there's some reading material for you to kind of go and learn more. So, alright? Perfect. Cool. So next thing
And
we
you
do.
can comment also, I saw.
Yeah, you can add your comments. You can say, oh, this is really beautiful. I hate this galaxy. This is my favorite galaxy. You can say what you want. Okay. Next, can I ask both of you to kind of come here again? Yeah, we're going to do this a lot. Don't worry.
I don't know whatever he
We'll
says.
stand
Yes,
outside
whatever
for the
they say.
dance.
He's the conductor.
We'll stand here.
No, you can take it.
Oh,
So this is releasing what? No, this is. Oh.
Yeah. So the telescope we talked about just now, as well as the eclipse in a box telescope Rekhesh talked about earlier, which is an Aditya, both were made in Hoskote in something called the Center for Research and Engineering, Research and Education in Science and Technology, CREST, and we bringing out a flyer which talks about that. Can we have the lights on? What is it? So this flyer is meant for engineering college students and so on. This flyer tells you what kind of very, very specialized equipment and rooms and facilities we have built in Hoskote so that we can make extremely precise and extremely clean telescopes to be sent to space, okay, in the MGKM Menon Laboratory for Space Science. MGKM Menon was a very famous physicist in India. He was the second director of Tata Institute of Fundamental Research. He was a very famous cosmic ray physicist. The laboratory is named after him. And therefore, we would like to also take this occasion to release this flyer to let people, especially engineering college students, engineering college teachers, companies, etc., startups, to come and talk, to know what it is we have here. We have world-class, state-of-the-art laboratories in Hoskote to build space telescopes, like any other country, like one of the foremost facilities other countries have. And therefore, this is something we're obviously proud of, and we want to show off a little bit, right, with this flyer. Okay, right. Thank you so much, Dr. Isha and Seetha.
And Aditya L1 was
Also assembled here.
And VSC payload was assembled.
Yeah. So Dr. Seetha, I'll introduce later. I also wanted to quickly introduce Dr. Professor Ishwar Reddy here. He's an astronomer here. He's the Dean of the Faculty of Sciences at the Indian Institute of Astrophysics. And his specialty is stars which have weird chemical properties, right? Yeah. Especially stars which have too much lithium compared to other stars. And he's one of the world's experts on that. He also is the person leading the India's contribution to building one of the world's largest telescopes with optical, which is coming up probably in Hawaii, called the 30-meter telescope. 30-meter telescope will have a mirror which is 3 times as large as the largest telescope we have on Earth right now. And he's leading the project from the India side. And if you want to talk about both of them, you can catch him later at tea break and have a chat with him. Yep. So, Professor Ishwar Reddy. Thank you. No, don't go. Okay. Next, we come to something the students are looking forward to, which is the prize distribution. Seetha, also please. Prize distribution for the quiz. So we had a quiz in the morning. I think everybody here was either a part of it or was at the back cheering them on. We had 14 teams from schools across Bangalore, and it was fun. Was it fun? Yes. Yeah. So we first going to distribute the participation certificates to everybody, then followed by the prizes. Now, participation certificates, everybody is going to get a certificate and also going to get a envelope which has stickers and flyers about what you saw. Right? So some merchandise, some cool stuff for you. So you can I ask the quiz winners to kind of come here and line up. The first is Moraji Desai Residential School, Chamarajpet. And get your envelope.
Yeah, I think we should be standing there.
You can come in front. Yeah, come here. No, this is photo. Get this. So you have to give it your pass onto that.
These are the envelopes and certificates.
So you give them an envelope.
Are there names in this?
No.
No, he can give the certificate, I can give the envelope.
No, I
So both.
So first, Moraji Desai Residential School, Chamarajpet, Hemcharan Teja and Harshavardhan Reddy. Then you can pose for a photograph.
Now we can give this as well.
Next is Moraji Desai, Adakamaranahalli. After it's Carmen.
Okay, thank you, congratulations.
After it's Atibele. Okay. So next is Arjun and Rahul from Moraji Desai Residential School, Adakamaranahalli.
Arjun?
Then Carmel, then Atibele, then Sudarshan.
We can announce, while he's taking a photo.
Then can I call on Janavi R and Diba Anya from Carmel Public School? Both your own training squad is there.
As you can see,
After Atibele.
looks like I have a lot of fans here.
And then
Congratulations.
next we have Manasa R and Darush K from Moraji Desai Residential School, Atibele.
Manasa?
ICSE Sudarshan. Next we have Tanish Gubba and Samat Vivek from Sudarshan Vidya Mandir ICSE.
Okay, the first name and
Face the camera.
we give the first
Then we have Gatik Sapra and Vatsal Sharma from National Public School ITPL.
Sapna?
Sudarshan CBSE.
मैं फोन कर रहा हूँ
Congratulations.
Next we have Naina Sameta and Dhairya Darpan Shah from Sudarshan Vidya Mandir CBSE. Police. You want? Police Public School.
Congratulations.
Then Ananya and Dhruva from Police Public School.
Congratulations.
Then we have Surabhi Kumari and Kavya from Shishu Mandir.
Surabhi. Congratulations.
Then we have Aditi Nair and Shumangini Sahu from Sudarshan Vidya Mandir CBSE. Seetha.
Oh, they're not here? Yeah, I think they've left, is it? Yes, you can collect it. We are collecting for it.
Oh, okay. Come.
Yeah, you can come here, you can collect both.
Now the prices.
Yeah, bonus.
Congratulations.
Now we come to the winners. They are there. So third prize goes to Sudarshan Vidya Mandir CBSE team, Dhairya Darpan Shah and Naina Sameta.
Yes.
So the prize is a book coupon from Sapna Book House.
This is 9.
I hope you get a good book.
You can buy any book, you don't have to buy an astronomy book.
Yeah.
Second prize goes to Sudarshan Vidyamandir ICSE, Samat Vivek and Tanesh Gubba.
Preferably any science book.
You get one more.
You will take this as well.
Yeah.
Oh, okay. And this one, second place.
Sama?
You have the names?
Okay.
Congratulations.
And the first place goes to National Public School ITPL, Vatsal Sharma and Ganesh Saha.
And these two release certificate for 1 months.
We also want to especially congratulate the people who came fourth and fifth. So I have a little bit some more stickers and badges for you. So fourth place is Morali Desai Residential School Attibele, Manasa and Dhanush. And fifth place is Carmel Garden Public School, Janami and Lipa. Is St. Francis here? St. Francis is here. RPNM is here. RPNM is here. Do you want to collect the certificates for? I thought you already. Okay. Come. Then, so we thought RBN had already left.
Before
They
that,
not.
you announced 2 more people for the fourth and fifth.
Give it. We also want to give participation certificates for RBNM Girls High School. It was not left. We thought we took it already.
Sir, this
Girls High School.
Seetha?
And Varun and Mokshatna from RBNM Boys High School.
Mantis.
St. Francis has left. We'll give them the certificates later. That's all. Great, fantastic. So congratulations everybody, all the winners. Fifth place was only one.
No, 50 year. 50 year.
That was 1/4 and 1/5. We had put both. We had put 2 in.
Yeah.
Yeah, we put 2 copies. So the fifth one has to go to Khan. It says. Yeah, sorry. Yeah, the fourth one will but we put 2 copies of it. Okay.
We made our national zero Sunday. Today is my program being broadcast in this place.
You will talk to the
I'm likely to.
Okay, so thanks everybody again. Congrats again for the prize winners, and we'll take a short tea break for people online. We are running 10 minutes late, so we'll meet at 4:05 again here. 5 we'll give it 5 minutes extra. At exactly 4:05 we'll meet here again to hear the public talk of Dr. Seetha. So please join us outside for tea and biscuits. And people online, you can just stay. The link remains the same. At 4:05 we'll begin again. Thank you.
Good arrangements.
Thank you.
Please ask me.
Certificates are not given.
Oh yeah, because you registered late. No, I'll write it for you by hand. Yeah, we had made the certificates by the time you registered, so let me just write it by hand. Ma'am, I'll just finish this and yeah. Tell me your full name.
Komal Das right.
Can you spell it for me?
K-O
K-O
M-A
M-A
L-A
L
A
L-A. Okay.
Das D-A-S
D-A-S.
Y-B
Y-B, is it? Separate initials?
Inches.
From?
Kittarandi Channama Residential College.
K-I-T-T-U-R, no?
Yes, sir. R-A-M-I.
Sorted?
C-H
Yeah, one. Yeah.
double M
Spelling mistakes, sir. There's no H.
A-double-M
But I think the names you sent us is for
Residential College. Hey, I'm in the school.
Residential, no?
Yes,
Okay, what is
Okay.
R-E-S-I
It's not spelling mistake, you have one extra. No?
Yes, yes.
N-T-I-A-L.
Thank you.
Everybody else, please join us outside for
College,
the
right?
and we'll come back in at 4:05.
C-O C-O
So you can just take a screen capture. For students who are not allowed your cell phones, you can catch me later and we'll send you the link. Or get a teacher to get the link and send it to you later.
What do you? Zoom, it's not yet shared.
Yeah. Next.
Again. Share full screen.
Is it unmuted? Unmuted. Okay, so for people online, you can click on the QR code to join the WhatsApp group. It's an announcement group. Only I can post, so none of you can say good morning, good afternoon, good evening. Okay. So you only get announcements about what we're doing here, right? So we'll give it another few minutes and then we'll start. In the meantime, has everybody taken this on your phone? Yeah? Where is the formula?
Share the screen.
Zoom share. Windows system. No, don't start it. Just wait. Let's see. Just give it a few minutes more. So we'll begin this session with a short 2-minute video which we made for National Space Day, which kind of talks a little bit about what all we do, what all telescopes we have, so that you get to know a little bit about our institute without me talking about it endlessly, right?
There's no idea.
Some music. There's a paint. So this is what we do. We work here on pretty much. So you'll find astronomers in our institute working on almost every branch of astronomy, right? From the universe to stars to exoplanets to star galaxies to Big Bang to everything, right? And they do it using data from telescopes in India, telescopes abroad, telescopes in space. We have 5 observatories, 5 centers. One is Kodaikanal, which is 125 years old this year. Right? It's the oldest scientific establishment in the country. Then the Vaidova Observatory in Kavlur, on which there are questions in the quiz, which you can visit. And then, of course, our observatory in Hanle in Ladakh, in the mountains. Then we have a radio observatory in Gaurabednor, which is very close by. You can do a day trip of it. Then, of course, we have Kresh and Hoskote, where the space payloads you saw were made. These are the clean rooms and other machines we have to make sure that the space payloads are built to specification. And then we saw the ultraviolet image gallery being released just now. And Rekhesh talked about the eclipse in the box that we launched last year in Aditya. We also making mirrors for an international project I mentioned, which Ishwar is in charge of, called 30-meter telescope that we built in Hawaii. And we are now leading, we are going to build new telescopes, right? All these telescopes are existing, but we're going to build newer, bigger, better telescopes for the future, both in India and jointly in collaboration with people abroad as well. Okay. So that's a little bit, a small little glimpse of what we do at this institution. So now, I'm going to get the next talk started. The next talk is by Dr. Seetha. You already heard her a little bit before, earlier. Dr. Seetha is an emeritus scientist, an honorary member at the Raman Research Institute in Bangalore here. It's in Making Circle, if you haven't been there. She retired as outstanding scientist from UR Rao Satellite Center in ISRO in 2019. She worked in ISRO for 39 years. And she was the director of the Space Science Program Office at ISRO headquarters. The Space Science Program Office is the one in charge of all the astronomy missions. All the spacecraft sent to space which work on astronomy, the astronomy science part is handled at her office. And therefore she was responsible for the coordination of all space science activities of ISRO. She also did her PhD from IIA Bangalore long back on white dwarf pulsators. And you can ask her about that, she'll tell you a little bit about it later. Her research areas are study of variable stars in X-ray and optical wavebands, and therefore she's used telescopes both on the ground and in space, mainly in X-ray binary systems and the optical binaries and individual white dwarf stars. She's also contributed extensively to development of space science instrumentation for Indian satellite missions. She's also the principal investigator of AstroSat, which you heard a lot about. Which is the first dedicated space astronomy mission of India. She received many awards, just a few of them. The C. Raman Young Scientist Award in 2003, that was young indeed. The Best Woman Scientist Award in 2012 from the Astronautical Society of India. The member of the Team Excellence Award of ISRO for AstroSat Mission 2015. The ASI Zubin Kimbawi Award was conferred on the Team AstroSat for 2021, of which she was the part. And she is the principal investigator. Distinguished Alumni Award from the Old Students Association of Hindu College, Delhi, where she did her master's. Bachelor's in undergraduate. Okay. Therefore, I think she's the ideal person to talk to you about space missions in India, as well as astronomy being done since the very beginning by ISRO in its space program. So now I call upon Dr. Seetha to give a talk.
So good afternoon to all of you. So let me start where Rekhesh left off. As he said, we have a long beginning, starting from sounding rockets in 1960s. That was when we started experiments in both atmospheric physics and astronomy. These are the experiments which are flown on rockets, which have a fly, which can view the star only for about 10 minutes or so. And this continued till the 1980s or so, till we had our own satellites and launch vehicles. One thing is, so the top row, Aryabhatta, as he mentioned, was the first satellite built by India, and it had several astronomy experiments, like X-ray astronomy experiments, and also one was gamma ray and so on. So the next one was in Bhaskara, we had a monitor, X-ray monitor, and that was also one of them. SROS C2 was a gamma ray burst, he already mentioned. Indian X-ray astronomy experiment, we viewed several X-ray sources. First one to actually point to specific source in the sky, and then we had the solar X-ray spectrometer on GSAT-2. So we used low Earth satellites, we used polar satellites, we used geostationary satellites. These last three were piggyback, what we call piggyback experiments, because they were piggybacking on a satellite which was meant for other purposes. The bottom row is the full of missions, specifically which you would have all heard about, because when we started flying missions, we became very famous. So Chandrayaan 1, Mars Orbiter mission, AstroSat, Chandrayaan 2, Chandrayaan 3, and Aditya L1. And we also have the ExpoSat now, which was launched in 2024, January 1st. So with these, so today I will be telling you about some of the results which we have got from these missions. Today being the anniversary of Chandrayaan 3. So we will start with the lunar results and then we will go on to the other missions. Yeah. These are the recent missions: AstroSat, Chandrayaan 1, 2 and 3, Mars Orbiter mission and Aditya L1, and I'll be talking about them. So, about AstroSat, you heard that AstroSat is a dedicated mission for astronomy. After all those piggyback satellites, scientists were able to convince ISRO that we need a dedicated mission for astronomy, and this is the mission which was flown in 2015 using PSLV, but PSLV launched this satellite in a near equatorial orbit. If we go in a polar orbit, we have a lot of charged particle background, which is not very good for X-ray instruments because they detect X-rays and charged particle, and the charged particle becomes a background for the detection. So we want to eliminate that. So we launched this. This satellite is in a very, very low inclination orbit of 6 degrees and at a 650 kilometer altitude. It has 5 instruments. UVIT is from IIA and proposed. And the one thing which is special about AstroSat is this is the first mission which we have made it open to observations from any scientist all over the world can propose for observation using this satellite. So it's a proposal-based space observatory. Yeah. So let me just talk to you about the results from AstroSat briefly, few results only. Mainly the results which are coming from IIA because this is the host institute which built the UV imaging telescope. So one of the results is that we have studied many clusters of stars. There are 2 types of clusters. One is called open cluster and one is called globular cluster. In open clusters, there are hundreds to thousands of stars and they are a little more widespread compared to globular clusters. Globular clusters, on the other hand, are very, very compact and they house thousands of stars, thousands to almost 10,000. You can have several stars within a very, very small area of few arc minutes. Yeah, I'll be talking about this arc seconds and arc minutes. Arc second, as I already told you, is about 1,800 of the diameter of the moon, and arc minute is 60 times that. Yeah, so just like you have degrees, you have hours, minutes, seconds in time, you have degrees, arc minutes, arc seconds. Yeah. Okay, so So we imaged several globular clusters and open clusters. These two are NGC 188 is NGC 288 is a little less dense globular cluster compared to NGC 1851, which is, as you can see, very, very dense. And these are the outer parts of the globular cluster, which we can resolve these stars in FUV. And you can even resolve some of the inner stars in FUV. And this was one of the aims of building, in fact, UVIT. So this contains several thousands of stars. It's believed that these clusters have a common age and they evolved together. Now when they evolve together, we have something called the HR diagram and they turn off in the HR diagram. I won't go into those details. But from that turn off, one can find the age of that cluster. But one surprising thing in many of these clusters is as the cluster grows older and older, I already told you the blue objects evolve much faster. They are hotter, they are more massive, but they burn off very quickly. They have an age of few million years. Whereas a star like our sun has an age of 10 billion years. Okay, it can live up to 10 billion years. So, and a redder star, which is less massive than the sun, can even have a longer age. So these blue stars shouldn't exist in the very old clusters because they should have evolved and they should have become giants and so on. But we find that when we plot this so-called HR diagram for these clusters, we find something called the blue straggler stars. That's why they call it straggler, because they don't evolve along with the cluster. So they are blue straggler stars. So for long it was thought, do they belong to this at all, etc. So finally it was found that they do, in fact they do belong to that cluster, but they are blue and they are massive. So how did they come to remain massive and remain as blue? So that was one of the problems which we have sort of addressed with the UV imaging telescope, and we find that many of them are actually members of a binary which has a small low mass white dwarf as a companion, which we could not detect till now, but with the far UV flux which we could measure using the UVIT, we find that unless we have the white dwarf included, we can't fit the whole spectrum correctly. So that's how we find that it must be having a very low mass white dwarf as a companion. So this is a cartoon which tells you, so we start with this. How can you be so young if all are born at the same time? How did you get that extra mass? So shall I tell you my secret? There are two main scenarios. One is that several of the young stars actually became red giants, but they had a companion which was a little yellow star, and this red giant therefore donated mass to this yellow star, and finally what happened was this red giant became a small mass white dwarf, whereas this, which ate up all this mass from this red giant, became a blue massive star. Yeah? So she called it a vampire star. So we're finding actually many extremely low mass white dwarfs as companions based on only spectra. We can't image them. They're very close, they're very faint, we can't image them, but from the spectrum we can detect that there should be a bluer star compared to this star. And then the other scenario is, especially in dense regions, I told you some of these globular clusters are very dense. In those cases, they might also form due to collision itself because they are packed so well. So two stars can collide and they can therefore form a blue straggler. And then if you want to know more about blue stragglers, study more of these clusters, and lot of the students from IIA have done a lot of studies in several of these. Yeah? Okay. Then, if you think IIA has done only stars from UVIT, No, they have also done galaxies, and I have actually presented the first object which we saw, NGC 2336, in many forums. So I avoided that. There are many such galaxies where I told you in the spiral arms we find several star forming knots. We call them knots because it's not all along the spiral arm. There are specific regions where there are star forming regions, and they are particularly easier to identify in ultraviolet, and that's where the UVIT speciality comes. This is one of more recent results. This is actually there are several regions where there are several galaxies which are in a cluster, and many of them actually merge gradually over millions of years. They will come closer and they can become interacting galaxies, and finally they might merge. So when they are interacting, the big thing is the tidal forces come into picture, and they will pull out gas, they might push gas in, etc. Lots of tails form and so on. So when the gas gets disrupted, again there can be newer regions where star forming can take place, and several such pictures are there in the thing he showed, atoms for galaxy 7252, etc. etc. Now this, and the advantage of studying these clusters is that there can be supermassive black holes forming in these regions, which can then become nuclei for active galactic nuclei. Active galactic nuclei are huge galaxies where the nucleus shines much more brighter than the whole galaxy. That's why they are called active galactic nuclei, and there are of course jets, etc. also formed. So now these regions can actually host supermassive black holes, and they can become active galactic nuclei in future. So here are two galaxies, NGC 7734 and NGC 7733, and these are known to be interacting galaxies. And we also find, so this was studied in UV, it was studied in H alpha, and it was also studied in infrared using the South African telescope, South African Astronomical Observatory, a telescope there. So we find that this portion we put in this red box, there is probably another third galaxy, it is different from this galaxy, even though it appears to lie on the spiral arm of this NGC 7733, but actually it's a different galaxy, and it also most likely has a supermassive black hole, and therefore this might become a triple AGN system. Double AGN systems itself are rare, but triple AGN systems are rarer. Why are they important? Because you can then study how merging affects the formation of these galaxies and interaction and so on and so forth. And there is one fourth galaxy which is here, fairly distant, but in the UV we find there might be a bridge. Because of this merging, there might be gas flowing towards this galaxy also. Yeah, so these are the findings from this group of galaxies. So now, coming back from the stars and galaxies, I come back to Chandrayaan, which is the main aim of this today's day. I'll start from Chandrayaan 1. Why? Because I'll tell you why Chandrayaan 2 has similar instruments and so on. So Chandrayaan 1 had 5 payloads from India, and actually this was one of the satellites which had international cooperation, and it had several payloads from abroad, NASA, ESA, etc. And one of them was called MQ, Mineralogy Mapper it is called. So Chandrayaan 1, one of the things was it had the best 3D resolution. You could make maps, 3D maps at that time, which was 5-meter resolution when Chandrayaan 1 was flown. And this moon mineralogy mapper actually mapped several regions of the sky of the moon, and they found that the blue regions are all regions where OH or H2O. It's a mineralogy mapper, okay? So they can find the hydroxyl component or the H2O in the minerals. So that was found in all these blue regions. So you can see that the polar regions have a lot of blue regions, and also that it's not only the poles but also the mid-latitudes. You can see that this one is a spectrometer, and there is a water or an OH line which is around 2900 angstrom. This is for the better informed people. And the instrument itself could measure only up to 3000 nanometer or 3 micron we would say. So this line we could measure only part of it. The gray portion could not be addressed by this instrument. So as you can see, the actual observed line, this is a modeling, this is the observed line, and you can see that the lines are all cut off at 3 micron or 3000 nanometer.
Excuse me.
So,
Explain the colored strips where they came.
This one?
No,
This one?
Yeah.
Yeah, okay. So these strips are where Chandrayaan 1 actually covered the whole moon. The black strips could not be covered by Chandrayaan 1. So we couldn't cover the complete moon. The red ones are iron-bearing minerals, the red portions. And the green portion is the spectrum at 2.4 micron, at which this instrument was very sensitive. So, the blue is the minerals which have H2O or OH, and red is where iron is there, and green is where 2.4 is maximum, 2.4 micron or 2400 nanometers. These colors are for different latitudes. As you can see, this is higher latitudes and this is lower latitudes. And you can see that in the lower latitudes, the absorption feature is less intense compared to the polar regions. Yeah. In addition to that, on Chandrayaan 1, we had a moon impactor probe, we call that actually crash landed on the moon near the polar region, and it's around 89 degrees south, and it had a mass spectrometer. It observed the moon only before it crash landed, few minutes. So this is before the thing crash landed, and we could see features of water vapor. This is water in vapor form. We know that moon doesn't have an atmosphere like the earth, but very, 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 very low density atmosphere is there, and we could sense these water molecules. Yeah? Okay, next we go on to Chandrayaan 2. So, in Chandrayaan 2, of course, because it actually carried a rover and a lander, but that was a failure. But it had a very high resolution camera, and you can see this was resolution of 20.28 meters, so 28 centimeter, that big. Yeah, and you can see boulders, small pebbles, and craters. Yeah, so this high resolution camera was to image the landing site before it landed and to find out whether it is safe, the identified sites are safe. So this is the E crater region. It's very close to where we finally landed with Chandrayaan 3 also. And boulders are seen due to the ejecta from this crater. And I told you that we couldn't image the full line. Now the mineralogy instrument on Chandrayaan 2, which is still working, it's an orbiter. So it actually does work till 5 micron. So we can get the complete line till 3 micron. Yeah, beyond 3 micron is somewhere here. And so we are continuing to measure where the water is in different, and we can also identify where different types of regions on the moon where water is. And then other results from Chandrayaan 2 are we carry an X-ray spectrometer. X-ray. So while the mineralogy mapper actually maps minerals, they can't identify. They can only identify what type of mineral is it, and therefore what it consists of. Okay, from ground-based observation. Whereas the X-ray instrument, it's a fluorescence instrument, it can actually identify the atoms from fluorescence spectra. Sunlight impinges on the lunar surface and some of these atoms actually fluoresce. They will emit an X-ray photon which is very characteristic of that atom. And so you can actually find magnesium, aluminium, silicon, oxygen, all these lines, calcium, etc., and including the ion line. Okay. Now there is effort to actually combine the atomic data and the mineral data and then to compare and see whether they are matching, whether there are any differences and so on. Because you are also trying to find abundances of these elements and see. So one of the findings was that sodium, which was there are several sodium-rich places on the moon. This is the X-ray sky monitor, because I said sun impinges on the moon and then creates this. But you should know what sunlight, what is the kind of spectra which comes from the sun, right? Because you have to eliminate that. So for that we have a solar monitor, and it is a very high resolution. You can get temporal profiles. This is time, whereas these are all spectra where this is energy or wavelength. This is time versus counts or flux. So you can actually find how bright the sun is becoming due to flaring. And so this is 2019 to 2020. You can see several flares. Sun, by the way, many of you might know, follows a 11-year cycle, and it becomes very, very active during the peak of the cycle, and the peak is in 2024-25. So that's why the sun is very, very active in the last few years. And so you can see this is like a light bulb. If I plot the brightness of a bulb, which goes from dim to bright and then comes down, this is how the plot would look like. Okay, so this is what we call a light curve. Then I go on to Chandrayaan 3. Chandrayaan 3, remember, had only a lander and a rover, and in all the certificates you have the picture of it. The lander had 4 experiments, the rover had 2 experiments. The lander had one specific experiment which was to actually find the temperature below the surface of the moon. About 10 centimeter below it could go, and 1 centimeter at a time, measure, go down, measure, go down, measure. Okay, so this is the temperature. This is the surface of the moon, and as you go down, the temperature also goes down almost monotonically. Yeah, and what's special about this? Apollo spacecrafts have measured such things in the equatorial regions, whereas this is the first measurement in the polar region. Then there is a payload called LIPS, which is a laser-induced spectrum and ablated spectrum. So a laser is, the rover carries a laser, it pulses, and then after it pulses, you see the material is evaporated due to the laser, and we find the spectrum. The instrument studies the spectrum coming from it. And again, this is, you can study the lines coming from individual atoms. And remember, these are again in the optical region. And there is one more camera on the rover which measures it in the X-ray region. And we have compared these two. And we find sulfur in both these, from both these instruments from the rover. Okay, so this is one of the results which has just been announced on 21st August. It's a publication in Nature. So here I show how the rover actually went through this path from the lander to the rover, to the final point, and these white squares are where it actually stayed for a short while and did this experiment with the LIPS and the alpha-induced X-ray spectrometer. Both these are done one after another. So in the alpha-induced X-ray spectrometer, there is an alpha source which impinges alpha rays, and then due to that X-rays are emitted, and we study again, as I said, instead of solar radiation coming. So at each of these almost 24 points, these measurements were made, and you can see the spectra. These are two spectra. This is for a very short integration time of 20 minutes. This is for almost 180 minutes or so. And these are the abundances calculated for each of these elements. I think you can't read, but I'll tell you, this is silicon, which is of course the most abundant. And for example, aluminium is also very abundant. But we find that, for example, sodium, etc. are less abundant. And you can see iron is also not that, but comparatively more. Now, what is the result coming from this is that all this region where this is about 100 meters or so, wherever these were measured, the abundance is almost similar. So this region can be used for, in future, suppose you want to calibrate some instruments, you can use this region. Just like if we want to calibrate something, we actually use some portions on Earth which are found to be uniform. We measure ground truth from them. So this can be used, and we find that this what results we find is that it is almost what the lunar magma ocean theory predicts, that it is actually the minerals are stratified and that the lighter ones float on top. So they are actually anorthosite. I won't go into the details. So it supports the lunar magma ocean theory, but there is a slight difference that it has more magnesium than the standard lunar LMO theory. So there are variations of that theory which can predict also more magnesium. Yeah. Then I come to Mars Orbiter mission. Mars Orbiter mission, of course, had a lot of publicity. All of you would have heard a lot about it and so on. Again, we had a very highly elliptical orbit, and so we could image the Mars as a full disk within a few 400 milliseconds or so. We could image the whole of Mars because of the highly elliptical orbit, and therefore we could study a lot of overall science like dust storms. How do they travel with time? How do clouds form on top of these volcanoes? Mars has some of the tallest volcanoes in the whole of solar system, and so how clouds form. Are these waterized clouds or they actually carbon dioxide, because Mars atmosphere is very rich in carbon dioxide. So all that we could study, and this data, both Chandrayaan data and Mars data, is also made open to researchers all over the world, and people from universities have made use of this data alone or this data along with other data from other spacecrafts and published results. Then I finally come to Aditya L1. This is primarily to study very eruptive events. I told you we are in the time when there is a lot of activity on the sun, and we have to understand the connected processes. So there are a series of 7 instruments. The first 4 instruments actually look at the sun. This is one which is made in IIA. This does it in the optical, and one channel is in the infrared. This is made at IUCAA. It observes the sun in UV. This is X-ray, low energy X-ray, and this is high energy X-ray. Both of them made at ISRO, the UR Rao Satellite Center. These 4 look at the sun, whereas these 3 actually, these 2 look at the particles which come out of the sun during this coronal mass ejection, and they actually reach the L1 orbit. So in the orbit, what we call in situ payloads, they measure how much charged particles are coming from the sun during these events, and how it gets increased during these events. And if some of them are coming towards the earth, they can also give a warning that this is coming towards the earth, because some of the high latitude regions on the earth can get affected due to these CMEs, and there can be electrical breakdown, etc., etc. So any number of satellites which can give such warnings is useful. So and then we also have a magnetometer which can measure the magnetic field coming along with those particles. So now let me give you a brief result of this. I know many of you might have seen during May this year that there were lots of announcements in Google, right? That the sun is very active, sun has emitted a lot of coronal mass ejections, etc. Lots of flares. So you can see this is the X-ray. Again, this is a light curve. This is the time. This is from 8th May going all the way to 12th May. And you can see the sun varying by a large amount here. Okay, this is 1000, this is 10,000, and this is 100,000. Okay, so these which cross the 10,000 mark are very bright. They are called X-class flares. M class and X class are very, very bright, whereas A, B class, C class are fainter. You can also see some of the fainter ones, right? Here, and so on. Now, during the same time, around May 17th, this became very active, and so this is the image. Kodaikanal Solar Observatory actually gives images in H-alpha every day. Every day you can go to that website and see how the image of the sun is for the day. Okay, so why H alpha? Because H alpha actually is a better indicator of active regions compared to say just the surface. Yeah, so you can see these active regions. This is a black and white image, and you can see these white portions which are there. Now you can see a similar thing in magnesium. Of course, there's a color image and looks more attractive. You can see similar regions, right? But the advantage of magnesium is that the magnesium line is much more sensitive to these things, see these active regions, and they go a little deeper, more towards the chromosphere, and therefore you can see these active regions much more clearly. Just for you to compare, I am showing this image in a broadband UV. Broadband, it is still UV, but it can't measure the active regions as clearly. You can only see the spots, right? But it can't do. So this is where you need to have instruments with better and better capabilities in order to understand. Because many of you might think sun has been studied for thousands of years, right? Almost from when man was there, he has been observing the sun, either with the eye or during eclipse, etc. But there are different features you study in different filters, etc. So, and this is the magnetometer results from the same time. Again, it has remained quiet, and you can see suddenly becoming active and giving a lot of magnetic field at that time. So there are particles coming, there is increase in magnetic field reaching the orbit. So with that I will end my talk, and these are some of the important links. Some of you who want to do research, etc. can have these links. Of course, some of the images, Mars orbiter mission images are there in isro.gov.in. There's also actually illustrated book for young children, which is downloadable, describing about the instruments on Mars. There is also a Mars Atlas consisting of several pictures, so you can download those. There is this big book called Fishing Amulet to Red Planet. It's an e-book which you can read. This traces the history from the rocket days to Mars orbiter mission. And then, of course, AstroSat, we have, because it is made open for proposal, we have over 1,500 subscribers to the AstroSat, and publication list and other info on we have a science center which is hosted at IUCA, and you can observe these. Of course, data you can download from the same. This is called the Indian Space Science Data Center. It hosts all the science data from any of these space missions. So you can go to that, and you can go to AstroBrowse and see what is there. Yeah, so with that, I'll end my talk. Thanks a lot.
Thank you, Seetha. I think it's a wonderful talk. She not only explained to you what the huge history of space astronomy in India, but also what each space mission has taught us, right? We hear about Chandrayaan landing, and that makes us really happy. But then this is an occasion for us to learn what science it did. What did we learn from Chandrayaan mission? What did the scientists learn? Why do you want to go back again to it, and so on and so forth? I think it's fantastic. We'll take questions now for her. Just put your hands up, the mic will come to you.
Yes.
Yeah, come on.
Can you show the slide where you showed whether the Chandrayaan rover went, Chandrayaan 3 rover?
Although the sign-up sheet going on, please just sign. It's not mandatory. If you'd like to sign, please sign your name so that we have a record of who all came.
Yeah.
What are the colored dots?
Okay. So Vikram landed. This is where finally the Pragyan ended. Okay, the rover ended there. These are dots where there are information from the navigation camera, etc.
Yeah, questions? Yeah, please.
From results of Chandrayaan 3, you had the temperature, surface temperature. So, from within just 8 centimeter difference in the surface, there is a difference of 60 Celsius degrees. So, in the surface of moon is cold or hot?
Okay, it's both. The surface of the moon can be terribly cold, can be terribly hot also. Because, as I told you, the moon doesn't have much of an atmosphere. So there are no winds, there is nothing like that. So when the sun shines on the moon, it's very hot, of the order of 150 plus 150 degrees. When the night comes after 15 days at the same place, then it becomes very cold. It can go as low as minus 100 degrees or so. So that's why instruments which have to go and land there, and if they have to survive for very long, then they have to be able to survive these temperatures first. So we have now just measured these. I am waiting for a publication to come out of that payload. So the thermal, in addition to this, the thermal conductivity of the soil on moon comes into picture. Does it really conduct the surface heat down below, or does it not conduct? When the lunar surface becomes very hot, how deep can it conduct, etc. Right? So all these, that is also being studied. At the polar regions. Again, this might vary slightly compared to the equatorial regions.
No, Chandrayaan 3 data is from equatorial region.
Chandrayaan 3 is from polar, near pole. Yeah, near pole, not the pole, because it landed near the pole. Apollo readings are from the equatorial regions.
Thank you.
It's a pretty sharp drop in temperature, right?
Yeah.
I mean, you can do it even here on a hot day. You can do the same thing. Experiment instead of on the moon, you can do it on Earth as well. You can take a thermometer, stick it, and then you can see that within a few centimeters, it becomes much colder than the surface of the soil around us. Right? Yeah. Other questions? Yes, please. Him at the back and then.
Yeah.
Now, through media, we have heard about like Chandrayaan 3 landed with help of IIA technologies. Can you explain on that?
Okay.
Safe landing, because Chandrayaan 2 has failure because signal mismatched or safe landing is not done. Like Chandrayaan 3 is using IIA technologies. Can you explain on that?
No, both of them actually used, I should say, because once the lander is separated from the orbiter, then it is on its own, okay, from 30 kilometers. And there are 2-3 phases how it should land. First, there's a very sharp drop, and then the slower. During that slower time, actually, there are navigation cameras which take pictures. They take pictures and they also transmit some of those pictures to ground, and you can compare. But there are some decisions which are taken on board itself. That's where the AI comes in. Even though it is programmed to compare, etc., that comparison is machine-based. So based on that, in fact, it went to the next landing site because a boulder was seen on the main thing. So it went to the next one and landed there safely. So we had the advantage of Chandrayaan 3 was we had a few more sensors We added few more sensors, and therefore the intelligence was improved for the decision making.
So whether I should land here or should hop and land elsewhere
Yeah.
was decided, by the lander itself without any input from the ground, right? Yeah, it was. Yeah, the person.
Yeah, simple question. Now we have sent the spacecraft to moon, so we know the surface temperature there. In area.
Oh, we knew the surface temperature earlier itself. I don't claim that the surface temperature was known by us. This was a probe which actually, I won't say drilled, actually it doesn't drill like this, but it actually goes like this, push with the motor. And therefore, it actually measures at every centimeter. The only advantage is this is the first time we are actually measured near the pole. Why? Okay, let me make it clear why it's so important to measure these differences. As you go towards the poles, there are portions based on the inclination of the moon's orbit and around the earth and the sun, etc. There are regions in the poles where sun is never shining. They are called permanently shadowed regions. Okay? So things become colder and colder and colder as you go towards the poles. If you actually measure the temperatures in the equator and the mid-latitudes and the polar, it goes cold. So that is one of the main reasons where you go towards the pole. Second, the moon doesn't have atmosphere. The mid-latitudes gets very hot. Water can vaporize. Even other things can vaporize like sodium. They are all called volatiles. So once they vaporize, the theory is that they can hop. They get transported on the moon's surface. Depending on the energy with which they come out during the day, they go to another region, and there can be some things which can go into permanently shadowed regions and remain there. And that is where you can find large amounts of water, ice. That's the theory. Okay? So this is transportation of volatiles. So it's important to study all latitude regions of the moon. Whereas you can find a lot of water ice, but you can't stay there because there is no sunlight. You need sunlight for power, etc. Yeah? So, one balances.
Do we know the surface temperature of Mars?
Yes.
Is it more than moon or less?
Okay. The surface temperature of the Mars. Mars, remember, it is more distant from the Earth, from the Sun. And then it has an atmosphere. The atmosphere is greenhouse gas of carbon dioxide, but pressure is less. So you really can't directly compare that. Is it just due to sunlight falling or no? Yeah. The excursion of temperature on Mars is lesser compared to.
I just quickly googled, on Mars, the hottest it gets is 20 degrees centigrade, the coldest is minus 153 degrees centigrade. But then, again, just like on Earth too, right? You measure the temperature on the equator, doesn't tell you anything about what temperature at the polar region of the Earth is too. It's the same way. Kumar, then we'll go.
On Moon, the excursion can be as high as 200 degrees centigrade, plus 100.
What's excursion, ma'am?
Excursion means if I take the difference between the highest positive and the highest negative. Yeah, the difference. Okay, excursion, sorry. I shouldn't have used the word excursion because that also has another meaning, right? Yeah. So the delta temperature, I should say, yeah. Difference in temperature between minimum and maximum.
Why did the Vikram land there? Why not between the pink square and green square there's a place?
Now you're seeing that place, okay. when we were calculating all this for landing, we had those images from Chandrayaan 2. These images from the orbiter, okay, and also from some NASA spacecrafts. So based on that, you have to decide where to land. So we didn't want to land into a crater because we may not have sunlight. We don't want to land near a boulder because that leg you might land like this. And we may also not want to have a tilted region where again we might be tilted. So all these were considered and therefore we decided on 2 spots, one main and one alternate. Okay. Now, yes, what you are saying is true. Now, in fact, now we can take, these are pictures taken from the Vikram. There are many pictures taken from the Vikram lander itself and they are better to show the.
It seems like Vikram is close to some small crater.
It is not close to some crater, okay. Actually, there is this crater. There is this crater. You are saying this?
Yes.
Okay, this is a dip in the region. Yeah. It's not, maybe not a full-fledged crater, but yes.
But even that photo or the certificate where, the photo from the rover taken from of the lander very far away, there's a dip. There's a dip and then it goes up. Right? You can.
I think there's a certificate.
Yeah, this famous photo. If you look at the full frame of this photograph, you would see that there's another photo like this where the lander is a bit higher altitude and then the rover had come down a bit. So there's a gradual slope. No? That's what you're talking about, right?
Yes.
So, ma'am,
In fact, now that you asked this question, now I have to tell you. This result also tells that they measured in all these regions, right? And then when the rover went, they sometimes backed to the rover and went and measured and so on. So they find that these measurements not only match what is on the surface, but also match what is there at the portions where the rover went, which can dig up a few centimeters, right? Because it has gone away. So whereas the alpha particle spectrometer actually can go only few millimeters. It can penetrate only few millimeters, the alpha particle. Okay? But now it's like a tire going on top, so it can rake up the thing. There also they find similar abundance.
Yeah, that was the question.
So ma'am, the region of the moon which is in the dark side, the surface is ice or it is a normal surface?
On the dark side?
Yes.
The surface also has ice, but I think there's a lot of ice beneath. Surface has ice because it is permanently shadowed. So now they want to actually image lot of these permanently shadowed regions. See the regions where there is sunlight falls cannot have surface ice because it becomes very hot. Okay?
So ma'am, the region, the land and above the land, both have the same temperature or it have the different temperatures?
No, it has different temperatures. That's what the Chastity experiment shows.
Yeah. Other questions? People on YouTube, you can also post your questions online on the chat and we can take them.
Ma'am, when we see the images, how do we find the insights like people that when see the image, this is crater, this is this part, magnesium, water. For any software is there or you map with the existing data and find the information insights?
What do you, can you repeat?
You're
No, for example, many of these craters are actually named and there are maps for these craters. Okay? So, now what is
other
the
items like H2O, magnesium, sulfur, and these are things anybody experiment and already done the experiment and data is with us, or by seeing the image we can identify.
Okay, first. Okay. It's not using the image, it's actually using the spectrum. This is a spectrum. This is energy versus flux. Okay? Energy or wavelength, whichever. In optical we use wavelength, but in X-ray we use energy. That's all is the difference. So this is a spectrum. I didn't go into that because Rekhesh had explained. We collect mainly three types of data. One data is image like this. Okay? It's easy to understand. The second is, I told you, a light curve, temporal. Time versus how bright or faint it becomes. That's called temporal. The third is spectral, where actually, to give you an example, we see sunlight as yellowish, right? We call it white light. When you pass it through a prism or a grating or a CD, for example, you see several colors, right? If you expose a CD with lines to the sunlight, you will see several colors, right? That is called dispersion, right? So it breaks up the white light into the constituent 7 colors. So 7 colors in optical. Similarly, if you can break up the complete X-ray energy into several such so-called lines, then those lines will be this, aluminium, magnesium, etc., etc., etc.
That means you upload that images to any software or?
No. Actually, the X-ray instrument does not image. This instrument, there are 2 instruments I talked about. One instrument from the orbiter, actually, sunlight impinges on the lunar surface. It excites the atoms. So the atoms emit an X-ray photon. That X-ray photon is detected by the orbiter. This is called fluorescence. Okay? Then you assign an energy to it. What is the energy you measure? So you keep on getting all these X-rays from that place and you make a spectrum like this. Wherever you see lines, then you identify. How do you identify those lines? Standard spectra can be made on ground. Ground, the instrument is calibrated also from this energy to this energy. Then with that calibration, you compare and see that this is this line and so on. That is orbiter. On the rover also, it's very similar, except instead of sunlight, alpha rays are impinged, and that the atoms absorb the alpha energy and emit an X-ray. That's all is the difference. But they don't image. Neither of the X-ray instruments image. Advantage of the rover is it goes to one particular place and does it. So you know from where the place is coming. From the orbiter, the place is rather large. Few kilometers, few tens of kilometers. 12 by 12 kilometers is what you can do best with an orbiter. Whereas here, you can do few meters. See, this is the scale. This is 10 meters or so. The scale is 10 meters. So you can see that this whole thing is about meters.
Next question.
Are the craters on the moon undisturbed by an X?
Not at all, not at all. In fact, there's a big project by which you can actually find the age by number of craters. Crater study itself is a very, very good subject. So, some of these craters are young, some of these craters are slightly older. And but when I say young and old, it's not yesterday or 100 years. Million years versus billion years. That's the only difference, okay? Some of these craters are formed very long back, some of these craters are formed few million of years back. And you can find, and the meteoroids keep hitting these, so they can also disturb things. So there's always disturbance. You asked for it, now I'm going to give you one more result from this paper, this latest paper. It actually says that olivine, I won't get into that. That thing which they have got now, the results which they have got now, indicates that there might be contamination from the South Pole Aitken crater emitted materials also, which is about 350 kilometers or somewhere farther away.
Thank you.
Yeah, also a question there from the students? No? Then in front.
Ma'am, I got to know that humankind could only see one part of the moon that's called as the visible part. There is also called as a darker part that no one could ever see. So my question is, all the moon missions, maybe Chandrayaan or missions from international space agencies, all the missions or their rovers landed on the visible part or the darker side of the moon.
Okay. Visible is only from our Earth point of view, and dark is only from what we can see. But actually, it's not dark. Huh? It's actually what we call near side and far side. Why we can't see it is because the rotation of the moon and the revolution period of the moon around the Earth is identical.
Rotation of Earth and
Rotation of the moon and it orbiting around the Earth is same, 28 days. So while it is traveling, it keeps on rotating and you keep seeing the same face. So you can't see that. But the Chinese two missions have gone to the far side.
The Indian one is not on the moon.
The Indian one is on the near side. Why we go more to the near side is because we need to communicate from the Earth. The Chinese one had another satellite to communicate, which was orbiting.
They landed on the first side.
Yeah,
The
they
rover,
landed.
Chinese rover on the first.
But then they had a parallel satellite which they could communicate to the satellite and the satellite could communicate to the
Soviet Union mapped the far side long back. Luna mapped it here.
with an orbiter. So that's only a far side. So far side also has, but only difference they find is that tidal interactions are more on the near side compared to the far side.
Other questions? You can ask any question about the moon, space, rockets, anything you want. This is your chance. To ask any question about space or rockets.
You made it only open.
Yeah. Anything. Biology, chemistry, history, everything. Yes.
Now you made it so open, you put up an hand.
Ma'am, what will happen to the astronaut who died in space? Who will die in space?
Who may die? I won't say who will die. We don't want anyone to die.
Space or moon she's asking about?
Space.
No, in space.
Because two people are stranded in the moon.
Yeah, we want them to come safely back. All spacecrafts, I won't even tell astronaut, right? All spacecrafts which are in the low Earth orbit, actually they can come down. And then because the Earth has an atmosphere, they'll get more and more heated more and more as it comes down. So suppose a satellite is there at 500 kilometers, it will gradually within a year or so, it will come down because of the air resistance. We call it a friction in the air as it comes down. So that friction itself will cause it to heat up and it will burn. But large satellites like Space Lab, they cannot burn. So they will finally land somewhere. Luckily for us, On the Earth, 3/4 of the area is ocean. So often, and if you have a little bit of control, if you can communicate, you can make them land in the ocean. Yeah, that's what you do. So, but many of the small satellites burn up.
Like I said,
That
you can
is
ask
why
questions about anything.
Okay, so for example, Kalpana Chawla, their thing was small and it had a heat problem and so it burnt up, right?
Many Indians have went to Earth, Moon, but no one entered.
Indians, nobody has gone to moon. Yet.
Spacecrafts.
Spacecrafts, yes.
They went to Moon, but no one stepped on Moon. Why? No one stepped on Moon.
No Indian person has gone to circle the moon. There's only one Indian astronaut so far who has gone into space, and that is Rekhesh Sharma, but he has gone into a low Earth orbiter, not lunar orbit.
There was no human mission.
It was not even with NASA spacecraft. With NASA spacecrafts, humans have gone, and also Russian spacecraft, humans have gone, but no Indian yet. Even now with Gaganyaan, they will only go into lunar, to the low Earth orbit. They will not go to the moon.
I think ISRO has declared 2040s or so they want to put a person on the moon, right? That's the idea.
That's why they're working on a Chandrayaan 4-5 kind of thing.
There'll be Chandrayaan 4, right? Do you want to say something about that?
No, I hear what is in the news that the design etc. of Chandrayaan 4 and 5 is completed.
Yeah.
So, ma'am, in the absence of oxygen, fire does not ignite. So, if we blast in the space any nuclear bomb or any type of bomb, so will it explode?
Nuclear bomb, okay.
I said all topics, I'm sorry.
Now you asked for it and I'm going to give you a long answer. There was a treaty in 1970s that nuclear treaty, that nations shouldn't explode things in the atmosphere because if it spreads, that nuclear cloud after bursting, if it spreads, it will affect many countries. You know how the atom bombs in Nagasaki and Hiroshima have affected the people living there, right? But it was localized. But if it is done in the atmosphere of the Earth, then it will spread. So there was a treaty. Wait, I have not completed this. You asked for it, so I am going to give it. So there was this treaty, okay? So now, having made the treaty, now people said, how am I going to make sure this treaty is followed? What if somebody bursts and we don't even know? So there were a series of satellites called the Vela satellites, VELA. Satellites launched to actually monitor if there are such things. Okay, so they would have detectors looking towards the Earth and see if there are any nuclei. These were gamma ray detectors. Okay, and these gamma ray detectors were the ones which discovered the gamma ray bursts in 1975. Okay. They didn't find anybody violating the nuclear treaty, but they found this thing coming from space. And when they had multiple satellites, they could actually identify it is coming from outer space, and that was the start of the gamma ray burst area of research. It is still not closed. 1975, still not closed. We know they are coming from very far distances, cosmological distances. They may be due to gravitational wave sources, There may also be some supernovae, hypernovae. So,
But he also, I think, wanted to know if there's no oxygen, will it burn in space? Is that also?
it's not like burning,
Yeah,
right?
so nuclear bomb
Nuclear
doesn't
bomb
really
is
explode.
not, yeah. It's called fission or fusion. The sun doesn't have oxygen, right? How is it bright? Burning bright. That's nuclear action at the core. So it doesn't need oxygen. That's what I think.
Yeah. So nuclear bomb, exactly. So nuclear bomb is not something burning the way we
Yeah,
burn things,
we-
right? It's a different
we
kind
call it
of
burning
release of energy.
because of the energy and the heat and such things, but it's not really burning in
So it
the
doesn't need
chemical form.
oxygen. But her point is, even though it doesn't need oxygen, you shouldn't do it anyway. That's the point,
Yeah.
right?
Yes, again.
Can you make satellites that go into the sea and come back to land? Like
It won't be called a satellite, right? It would be called a submarine.
submarine that went into space and came.
Space, no.
No, you want to go to space or you want to go to sea? What is
Sea.
it? Want to both?
No, go to space and recover the satellite by making it go from sea to land.
That's how they are.
That's what they do.
But not landing on
Actually,
some
recoverable satellites which come back, which can come back to Earth, will either land on sea or will land on Earth. So many of these satellites, for example, Gaganyaan, for example, the people who go to space station, they come back, right?
Yes.
That lands on the sea or on the land. And Gaganyaan will also, the first few will land on the sea. Later they might have something which can land on the earth. The recoverable satellite which we had is RE, which India had around 2013 or so. It landed on the sea. In future, there is a recoverable launch vehicle that might land on the land.
So I
So you
think,
can do
I think Yuri Gagarin probably landed on land, right? But Armstrong and
But I
Aldrin and
feel
Collins
like
landed on
carrying it
sea.
with a helicopter.
Not actually, yes, a helicopter is also there. There's also just like the helicopter has what is called what is that? Chute. Parachute. It has a parachute which goes horizontal to break the velocity, to stop the velocity.
I mean, like it lands in it goes in the sea and then it kind of like swims back.
No, it floats. It'll have balloons. It'll put out balloons.
Someone else
has to come and take it.
Initially,
Is it possible to make something like this?
Oh, I had a slide on this actually. I didn't.
No, so it'll float. It'll. For example, when Neil Armstrong, Buzz Aldrin, and Michael Collins landed back, they landed on the sea. But they had these balloons or something which popped out as soon as they landed, so that they floated on the sea, and they're bright in color, so that
And
others could see it.
then
And they came and
immediately a ship will come
they came
and they will
found it.
Take them back to them.
So it won't sink. It'll float on.
I know that, but is it possible to make it kind of like swim on its own back to land?
Oh,
Then you need to have more things, no?
Then what
That
more?
adds weight to the satellite. You don't know.
you go pick it up. Swiggy will deliver satellites. 1 ounce to not to be delivered. Yes, there.
Yes, one more nuclear bomb.
The person here, then her. No, him, then her, then the person on the back.
Yeah, 3 more last questions.
Ma'am, how did the scientists discover about black holes?
Again, you are asking an X-ray astronomer and that's it. See, originally the neutron stars and black holes were predicted by theory. Okay? But then,
Why were they discovered? Like, why scientists thought there was a black hole, or how did they find out?
I'm telling you. So in X-ray astronomy, so when you, so it was predicted by theory, okay? Observationally, if you want, the discovery was by X-ray astronomy. So one of the first black holes discovered was Cygnus X1. This name comes from, Cygnus is the, what do you call it? Constellation. And X1 means the first brightest X-ray source in the cosmos. So this one actually showed variations which can be under milliseconds, and you can't have a c into t, c being velocity of light into t being under milliseconds, done with a more compact object. With a large object, it has to be a compact object, and therefore that was the indication first in X-ray astronomy. Second was, it had a binary companion. They could detect that companion in optical. Okay, this was an X-ray binary. So they found that the orbital periods of both that X-ray emitting star and the optical companion was the same. Therefore, this is a companion identified. Then, because they could identify the optical companion spectral type, they could estimate its mass. Once it is estimated, using Kepler's laws, you can estimate the mass of the black hole. And that mass came out to be more than 4 solar masses. Therefore, it should be a black hole. That's the way the first one was deduced.
You can also go to our YouTube channel. There are a couple of talks given by astronomers earlier this year on black holes. You can also follow that. So the meaning of black holes. The person there at the back.
Ma'am, what is...
No, hold on. Her first. And then one more question at the back, then we'll stop. And then you call us, we'll come to your school and then we'll spend a longer time with you. Yeah.
Ma'am, why space agencies are sending humans when there is no danger in space?
Good question. There are two schools of thought actually. There are two schools of thought. There are in fact scientists who say you can do much better using robotic spacecrafts. Use robots to do everything, digging, everything, rather than endangering humans. The advantage of humans is they have this AI in their head. Right? You go to a place, you find something which is different from what you thought will be, you can take your decision. Whereas if it is robotic, you have to build everything into it, right? So that's the difference.
Ma'am, one more.
But there are people who think like you that why endanger humans?
Then one more thing, Indian space, that ISRO is sending Air Force pilots to the space. Why not astronaut?
What is different? What is astronaut?
Why not astronauts? Why not
who is
students who are studying astronauts? Why not they? Why Air Force?
Who is students who are studying astronauts? What do you mean by that?
The ones who are getting training to be an astronaut, why they are not?
Who is getting training?
First, like people.
Who? Which people? That's what. Where are the Indians who are getting trained for astronauts?
But why Air Force?
No, wait. You're talking about something which doesn't exist. You're talking about, there is no school of training astronauts from BSc level, right?
Means if I be an astronaut, means if I be an Air Force pilot, then I can be an astronaut.
Yes.
No, I think it's a misunderstanding. An astronaut is not an astronomer. They're very different things.
There is a difference. I think, are you saying astronomers and astronauts? Are you mixing these two? We are all astronomers. None of us are going to be astronauts.
I can barely go to Himalayas, but they don't send me anywhere. I'm an astronomer, that's different, right? An astronaut, the training you're talking about is exactly the training an Air Force pilot gets, right?
See, the point is like this. I'll answer in simple terms. To go into space, you know space is difficult, right? You already told, why are you endangering humans? It's very difficult to go into space. So you need a lot of training. The Air Force pilots already get some training to fly on the jet planes, fighter planes. Some of that training they already have. So it's easier to train them. That's all. And they are also having the physical and mental capacity to undergo the extra training. They also, the Air Force pilots also have to undergo training, by the way, for becoming an astronaut.
Neil Armstrong was also in the Air Force.
So it's easier.
So he wasn't a person on the road who said, okay, I'll go. He was actually, so most astronauts actually initially were from the Air Force, in the US as well.
In US.
Initially.
But then later, when they have more and more chance and they wanted scientists to go to do experiments, they trained people like scientists. They made them mission scientists, etc. And they trained them and they sent them. Yeah? So there might be a time when you may not be an Air Force pilot, but you might become an astronaut.
How many of you want to be an astronaut?
How many of you want? He wants.
Want to be an astronaut? Only 2. If you get a chance to go to space, how many of you would? They bring you back. If I say you bring you back, then how many of you would?
That's space tourism for you.
If it's affordable.
No, that's what. That's space tourism for you. Just
And
go
moon?
to space.
Moon? You don't want.
Moon and live there.
You don't want to go.
I want to be a pilot.
Okay, good. So let's end with the fact that everybody here wants to go to the moon. And thank Dr. Seetha. So we have a small gift for her.
We can take a
Old IIA clock. So let's thank to tell the time when she goes to the moon. So just thank Dr. Seetha again for a wonderful talk. Dr. Rekhesh Mohan for the morning. All the volunteers, put your hands up, Vikram, Pushpa, Sukesh, and others who were there in the morning. Yes, that's it. And I hope you added, at least your teachers have added yourselves to the WhatsApp group. So join us next time and hope to see you next time at public meeting. Thanks all.
And I hope you guys. I hope you all enjoy your day today. Yes.